One player faces one goalkeeper from 12 yards away, and once the ball begins moving, neither has much time to revise their plan. At first, this can look like a lottery problem, where old results tempt us to find a pattern, or perhaps like a forecasting problem, where enough data can reveal a stable tendency. Yet the goalkeeper may have studied the same way, same history, and adjusted. If the kicker's strongest shot goes to the left, the goalkeeper may cover that side, which makes the right side look safer, unless they expect a response too. Each thought changes the answer produced by the thought before it, so the real question is not whether thinking ahead helps, it is how far ahead the kicker should think before another layer stops improving the decision. To isolate a question, remove the stadium for a moment and keep only the recursion. Your choice depends on what you think other people would choose. Now let's play a game. Pick any number from 0 to 100, knowing that the winner will be closest to 2/3 of the group's average. If choices begin around 50, 33 would look most sensible, but everyone can see that coming. If choices cluster near 33, then the target falls down to 22. Anticipate that, and you might choose 15, then 10, and eventually 7. Repeating the logic without limit, while assuming everyone reasons the same way, and the target finally converges towards 0. 0 is what we call the equilibrium answer. Yet in a new room, it is often a poor prediction because people do not begin with the same model or stop after the same number of steps. The puzzle is not merely how deeply you can reason, it is how deeply the other players are likely to reason and whether one more layer improves your guess. Classical game theory asks which strategies remain stable when every player's expectations and responses fit together, and the guessing game produces a clean answer under those assumptions. Behavioral experiments introduce an inconvenient observation. People begin with different models of the other players. One person may use a rough baseline, another may respond to that baseline, and someone else may respond to the expected response. Researchers formalize these patterns through level K and cognitive hierarchy models. The levels describe strategies used in a particular setting rather than intelligence, and a deeper answer helps only when it better matches the people being modeled. Against a shallow strategy, extra sophistication can become extra error. The same hierarchy appears on the field. A simple policy directs the kicker toward the strongest side, while the next step avoids the goalkeeper's favorite direction. Another step then accounts for the goalkeeper knowing the kicker's preferred side and expecting a response to the scouting report. Any rule followed every time can eventually be learned. Game theory therefore often points toward a mixed strategy, an uneven distribution across practice options. A mechanically stronger shot can remain more common, while alternatives keep it from becoming an announcement. The kicker does not need to generate random numbers during the run-up because training can compress the distribution into a prepared policy before the ball is placed. The math model describes what a stable strategy will look like, while leaving open how a person represents the opponent. In competitive guessing experiments, deeper strategic reasoning was associated with activity in medial prefrontal areas involved in thinking about other minds. Computational work called the game theory of mind represented the task through two related inferences: what the opponent is trying to do and how sophisticated the opponent's model of the player might be. These findings do not reveal a neural dial that counts reasoning levels. Instead, they indicate that treating another person as strategic changes the information represented during the choice. Even this richer account has a serious limitation because an opponent is not a fixed object waiting to be measured. They learn. A basic learner asks what worked before. A belief learner estimates what the opponent usually does, and an influence learner goes further by asking how the player's own choices are changing the opponent's next response. In an analysis of 361 kicks from 37 major international shootouts, goalkeepers showed sequential dependence. After repeated dives in one direction, they became increasingly likely to reverse direction, while the sequence of kickers did not reliably exploit that pattern. The two sides occupied different learning positions because one goalkeeper experienced the sequence continuously, whereas each kicker usually contributed to one single action. The data came from players who were simultaneously generating and reacting to those data. Deliberation can now be modeled as another decision. One more step might change the predicted dive or separate two options that were nearly tied, yet the same step might construct a more elaborate opponent than the evidence supports. It also consumes time and effort while creating another opportunity for estimation error. Rational meta-reasoning gives the trade-off a formal structure by continuing a computation only when its expected improvement to the final choice exceeds its cost. There is no universal best depth because the useful stopping points depends on the opponent, the uncertainty, and the clock. Expertise changes the calculation by moving much of the work into training and scouting, where thousands of earlier updates can be compressed into a few practice policies. At that spot, the remaining question is whether another thought would still change the action. Eventually, one policy has to control the body. Evidence supporting competing actions can accumulate over time, and when the alternatives remain close, conflict can raise the amount of support required before either action is released. Human recording and stimulation studies suggest that communication between medial frontal regions and the subthalamic nucleus helps adjust this decision's threshold, allowing the pathway to function like a temporary brake while conflict remains high. The whistle changes the calculation because waiting now carries a rising cost. No part of this system certifies that the chosen opponent model will be correct. Commitment means that the competition has been resolved strongly enough, or that continued delay is no longer expected to improve the choice enough. A penalty kick contains chance, learned tendencies, and most importantly, another living person who is learning back. A useful model cannot remove that uncertainty, although it can reveal which assumptions produce a choice, how those assumptions should update, and when another update has stopped earning its cost. A good decision can still miss, a poor one can still score, and one kick cannot validate the entire model. The useful stopping point arrives when another layer is unlikely to change the action enough to repay its cost, and beyond that point, deeper thought is just another dream.